Hi everyone, welcome to this bootcamp session. I hope all of you can hear me loud and clear. Yes.
Yes, sir.
Great. So I'll just go ahead, share my screen. Just everyone just let me know if you can see my screen. 911 call analyzer detecting life-threatening emergencies.
Yeah.
Great.
Yes, you can
If
see your
anyone
screen.
has questions, the chat box is the place for any kind of communication. The audio is also enabled, but I would request you guys to let me complete a certain topic, a certain section of the notebook, and then you can ask a question, right? That would be helpful because we would complete some section and then take questions for that section. Right? In the process of the webinar, I will ask multiple times if you have any questions or not. You can ask your questions there as well. Okay, so let's start this exciting bootcamp session. Today, we are going to build a neural network from scratch that will be able to detect if a call coming to the 911, again, the US emergency helpline number agency, if a call coming to that particular agency is a fraudulent call or very high potential false alarm call, or it is a death call, right? People are going to commit suicide. They might call 911 before that, things like that. So we are basically trying to understand the seriousness or the sincerity of the call. And depending on that, we can prioritize where to send help first, right? Earlier, this would be analyzed by manual. This would be analyzed manually, where there will be people sitting on these phones, and whenever they get a call, they would pick up the call and they would try to understand the seriousness of the situation. I hope that makes sense, everyone. Initially, this was done manually, right? You would have to depend on the person picking up the call to have a good understanding of the seriousness of the call, and then allocate resources. But what are the problems with these kind of approaches? The first is there will always be limitations. If today you are getting 100 calls per day on an average, and you have, let's say, 120 employees with these telephones picking up these numbers or any of these calls, during this time also, the number of calls, if on a particular day become 130, then 10 individuals will have to wait for others to complete their calls, right? So you would always have to decide what is the percentage of employees you need extra, right? Compared to the number of calls per day. Now, this could be calls per day. This could be calls simultaneously, right? If 100 calls, 130 calls are coming simultaneously, you obviously need more than 130 members picking up or receiving those calls. Is that clear, everyone? Yes or no? Make sense? Great. Now, the immediate problem that all of us can see is there might be discrepancies between this value and our understood or decided value. If there's 130 calls, if we have 150 employees, that's fine. But if there's 200 calls immediately, we are not able to provide the emergency helpline service to 50 members of the country, 50 residents of the country. And that those 50 may be in a life or death situation, right? Just imagine someone has a hospital emergency, medical emergency. Someone has a poor mental health condition. They are alone at home. They might be taking some rash decisions, things like that. The 911 is a great way to just have that entire system where people can call 911 and completely have a solution for their safety and protection, right? Starting from criminal activities to medical emergencies, everything gets covered under 911. Now, because this is not a scalable solution. What is a scalable solution? Just imagine a company like Hotstar. When there is let's say there is any match on Hotstar, let's say the matches of South Africa versus Bangladesh. How many people do you think are going to watch this match? Or let's come up with a number X. Now another match is happening between India versus Pakistan. What would be a rough estimate for the number of people watching that match with respect to X? At least 2x, maybe 2.5x. If it is a World Cup final, it can be 5x also, right? Because the populations of people living in India, right, and Pakistan might be higher, and their cricket watching passion would be higher than these two countries, let's say. Now, Hotstar as a platform is a scalable platform. Why? Because no matter how many people are viewing the match, Hotstar will not give you any kind of error. It will not give you any kind of lag. Why? Because their system is a scalable solution. And this is the exact problem we are trying to solve here. Instead of having n number of human beings receiving the calls, if we could have an initial level filter on the seriousness of the call, our way of allocating humans, let's say, first a system, a machine learning model, an AI model filters out the serious calls, right? It allocates priority of calling and connecting with a receiver on the other end based on the seriousness of the call. So if there are 150 calls coming, incoming calls, and I have 100 people who can receive the call, so let's call them receivers. In this situation, I need a priority or a ranking algorithm. This ranking algorithm is essential so that I know which 100 people out of these 150 calls should I prioritize, or should I connect directly with a human, right? So our solution today is going to provide that initial level filter, initial level ranking, so that allocation of humans and corresponding allocation of resources is optimal for the US government. Is that clear? Problem statement, guys. All of you, I hope that makes sense. Great. What kind of data would we have? Now, a lot of you might have built or worked on or created projects in machine learning AI in the past. But very few people today have the experience of translating information. For example, if you would have worked on a natural language processing problem, you would have had converted text into embeddings, right? Embeddings are basically numerical representation of text data, right? So if you worked on an NLP problem at any point of time, you will definitely have converted text data into numerical data, because machines can only work with numerical data, right? If you already have numerical data, or which we generally call tabular data, in that case, you might have just directly used that data, right? Then there could be categorical data, but a very special kind of data set where a lot of people don't have any idea on how it works is audio data. Audio data is special because there are very few and very strict ways of translating audio data into numerical. Because first you will have to convert audio data into text data. Maybe you need this translation layer first, and only then you convert text data into numerical data. Or you could directly convert audio data based on the frequency directly into numerical data, right? The rises and falls of audio. Have you guys seen that, earlier when we had Windows, let's say at least 5-6 years back, there was Windows Media Player, right? In Windows Media Player, whenever we used to play an audio, there was a very fancy display. You guys remember that? Depending on the beats, the fancy display also adjusted itself. There were different kinds of histograms that would move while the music would be played. You guys remember that? Right? So how did that tool, the Windows Media Player, based on the audio, create that dynamic fancy display. It basically worked with the frequencies of the audio, and that frequency, it directly proportionated and displayed some fancy image. Colored bars that were going up and down, either darker or bolder, either they were increasing in size or reducing in size, depending on the audio frequency. So audio data handling and building a machine learning model with audio data is a very exciting challenge. Why? Because think about tools like Amazon Alexa, right? Amazon Alexa, then you have OK Google, then you have Hey Siri, right? The idea being all of these tools are actually going to work on the same logic. They will hear audio, translate it into text, take the text through a machine learning model or an AI model, and then the AI model will come up with steps or processes that needs to be executed. And these processes, once executed, will get the job done. For example, if I say that, set an alarm at this particular time period, so it will automatically follow the instructions. Why? Because first it heard me, then it translated what I am saying into text, then it used the AI model, which is already built into the system. And then that AI model gave steps and processes to be executed by the executor, which is, either it's Alexa or Siri or Google, right? And that lets you or helps you get the job done. I hope this is clear, all of you. Yes, no? Why audio is an interesting problem to have. Also, very few people have worked on problems like these, right? So today we are going to solve that problem. Okay, so I'll just give you guys a quick 1 minute to read this text that you see on my screen, and then we'll come back. This will give you most of the information about the project that we're solving. And don't worry, you will get this notebook, you will get the data, you'll get an entire zip file for you to explore and play around with this data as well. Okay, great. Everyone read this? Can we now move forward, guys? Guys, just a quick yes or no response. Great. So now the 911 calls have a lot of details embedded in them. Just think about the situation. If a new person, who in this case is called a dispatcher, or the 911 receivers, whoever receives the call, if you as an individual want to take that job, and your boss, your leader, or your let's say your manager asks you that go through a lot of these call records to understand which call is serious, which is not, how people behave, what are the different trends of handling these 911 calls. The first thing is, you will never be able to listen to, let's say, like 5,000, 50,000, 100,000 calls, right? Why? Because obviously You are a human. You have certain limitations. Even if you say that I will hear 10 calls every day, because you actually have to work also, right? It's not like you'll just sit and hear calls. So if there's like, let's say 100,000 minutes of calls received by so many dispatchers in the past from so many residents of the country, right? What you will realize immediately is that you will only be able to listen to, let's say 500, 1,000 or a limited number of calls. But a computer does not have that restriction. It can listen to millions and millions, hours and hours, minutes and minutes of data in less than 5 minutes or 10 minutes, right? That is why the importance of this increases. So let's look at the data set. This is my data set. There is an event ID which uniquely identifies the event. There is a link of this entire event, basically the call, the details, etc. We don't need that here. We already have the audio. This was the title: Detroit Child's 911 call audio, Girls Murder 911 call audio, Shoot Her 911 call audio, Snowstorm, Call for a Date, etc. etc. These are the dates given. These are the states in which that happened. These are the deaths that happened. There might be cases where there were no deaths. There might be cases where there is one death, or there are two deaths or more than that, right? Then there is potential death. What was the potential of death in that call? For example, if there are 5 people, the potential death was 5, right? But let's say eventually more people got dead, because during the call, I don't know what is the possibility of death. But when I'm on the call, I am logging the potential death. How many people can die, right? So there might be cases where actual deaths were higher than the potential deaths, right? And there might be cases where, deaths were lower than the potential death, etc., etc. The important thing here is this: false alarm. Was this particular alarm or this particular call genuine, or was it false? Right? What we need to find out by hearing a call, the system needs to find out, is this a false alarm or is this a genuine call that needs help from a receiver? Okay, and there are other details as well. Okay, let's look at one of the descriptions in this data quickly. df.log 0, description. Look at this. February 2006. 5-year-old Robert Turner called to say his mother was unconscious. However, dispatcher Sharon Nichols believed it was a prank call. Nichols and other dispatcher were later fired, and Nichols was charged. See, who was Nichols? The dispatcher. Nichols was charged with criminal neglect of duty. She was later convicted but granted probation. Also listen to the second. Let's say that's something. Let's look at another description. 911 call of a lifetime. Volusia County FLA dispatcher Donna Schifani talks to a 5-year-old Tia Henlin, who calmly reports her 2 parents shot to death. Right? So these are descriptions of the murder. See, there are bigger descriptions as well as smaller descriptions. Okay. Now let's take our data science, machine learning, and AI route. Now, like we've talked about the problem statement, we've understood why it is essential, why it's very important to solve this problem, how it is interesting and challenging. Now let's really get to the gist of solving the problem. Before we start, does anyone have any questions about the problem statement? Guys, let me know if there's anything. No. Great. So let's start our data science route. The first thing that we need to understand here is how's the quality of the data. So we check the missing values. df.isNull.sum, pretty simple. .isNull is basically going to tell you if there is a null value or not. Wherever there is a null value, this will be true. Wherever it is not a null value, it will be false. Because true and false are Boolean values, like true is basically Boolean 1 and false is basically Boolean 0, I can actually sum them up. So false summing 0 sum will be 0, but true summing will actually tell me how many missing values exist. So in my date column, there is 21 missing values. State has 8. I don't know the states of the call, 8 of them out of my entire data. What is the size of my entire data? df.shape, it's 710 calls. Out of that, I don't know state of 8 of them, date of 21 of them, and there is death, potential death, and false alarm for 111 of them. Description is 9. Now, what I need to drop is I am very interested and focused on the deaths column, right? So if I don't know the death, potential death, or false alarm of it, I can't work with it. For example, DF, I will just check for false alarm, things that are important for me, is null. And then I will just set the DF dot lock this value and false alarm. 39th row is null. So I'll just quickly check df dot lock 39. This is the event which has null values. Okay. And you can see potential death, false alarm, all of them are null. So this 111 is basically coming from a common row. Is that clear, all of you? Guys, I hope that makes sense. Right? So this is coming from a common thing. That is why I can just simply drop this. Okay. And here I'm just dropping, and I'm dropping based on the subset deaths. So based on the death column, if there is any null value, I will drop the entire column. I did that. Now, explore the death situation. How many false alarms were there in the data? See, false alarm, 1 means there was a false alarm, right? 0 means it was not a false alarm, it was genuine. Does everyone understand that? See, in this particular case, the first one that we saw, why is the false alarm 0? Because actually there was a death. The dispatcher thought it was a joke and they were convicted for criminal duty. I mean, criminal neglect of duty. Remember, everyone? I'm trying to keep everything, well knit so that you guys understand the whole process step by step. A 5-year-old said that his mother was unconscious. People thought it was a prank. And that is why they were convicted with criminal neglect of duty, right? So this was not a false alarm. That is why you see 0 here. Okay. On the other hand, this is a false alarm. Let's check this one out. df.log2. And I would like to look at the description of the second row, right? This is called as a false alarm. Let's see what it is. Caller reports her daughter is creating a disturbance at home, and the dispatcher makes an inappropriate comment, right? So this thing obviously is a false alarm. If your daughter is creating disturbance at home, that doesn't mean that 911 is going to give you a priority of service, right? This is not an emergency situation. So I hope everyone understood false alarm. Then what was the potential death and what was the actual death? See, there are cases where there were 15 deaths. There were cases where there were 25 deaths. Imagine the scenario where deaths equal to 25. See this particular row. Let's look at the description column of both these cases. Los Angeles metrolink.com, right? September 12, 2008, a Los Angeles Metrolink computer train crashed head-on with a freight train, generating many 911 calls from the passengers. LAFD released 4 of the calls. So these are the calls that were released. Not all of them were released, but there were 25 deaths. Shweta, we are not giving 25. I was just showing an example of, if there are deaths 25, there is a meaningful data. I hope that's clear, right? We are not giving 25. We saw the distribution of the deaths column to have this value 25. Now, whenever this happens, you will obviously ask, curiously, you will ask a question. There was a call to 911 where there were 25 deaths. How is that possible? That is what we just explored, right? State of California, false alarm 0. See why? Because this was a true alarm. Potential death here is 1 because one person called, right? According to the person who's listening to it, the potential death was 1 because one person had called, right? See, potential death 0, potential death 1. So in these cases, potential death is a column that we should ignore. We should focus mostly on false alarm. Another important aspect of this whole thing is when you look at this distribution, what do you think? Is this a good distribution for any kind of machine learning model? Any kind of pattern learning? Is this a good distribution for that? Right? It is not a good distribution. Shweta and Shubhankar are correct. The problem is this is imbalanced. A very classic example of that is, just imagine a situation where you are doing something, let's say cancer detection. Okay. Let's say you are talking about cancer detection. You are building a machine learning model and you get some data from the market. Okay. I mean, you go to different hospitals, you collect data of cancer, people who, what were their medical stats before they were getting, tested for cancer. And then ultimately, did they really have cancer or not after diagnosis? So we know the reality is out of 100 people, 1 may have cancer. On an average, out of 100 people, 1 has cancer. Let's say I put it that way. Other 99 people don't have cancer. Now think about it. Instead of building a machine learning model, I can try to act smart or play smart, and I can predict everyone who comes to my clinic. I can just predict that they don't have cancer. If I do that for a sufficiently large population, what will be my accuracy? Tell me. If 1,000 people come to my clinic and I ask my machine learning model to make a prediction on them, 1,000 people, if I predict everyone that nobody has cancer, then my accuracy will be 99%, right? Because out of these many people, 999 or let's say 990 people, right? 990 people will not have cancer and 10 people will have cancer, right? So I'll still be 99% accurate. But is there any use of this 99% accuracy? No. Why? Because it doesn't solve my problem in reality. It's not the correct solution to detect and solve my problem. Okay. That is why when situations like these arise, we have to be very cautious of data having any kind of imbalance. If I show my machine learning model or my AI model, my neural network, a lot of these cases, false alarm 0 cases, and very few cases of false alarm 1, then obviously it will learn more how to predict false alarm 0. But that completely disrupts my objective. I want to predict false alarm cases better. Clear, all of you? Any doubts so far? No? Great. So how are we going to load the audio? That's the primary question, right? I mean, the first time you're dealing with audio data, let's say, how do you do audio data loading and translation, transformation, conversion, whatever you'd like to call it, of those audios into features, numerical features? Okay. So librosa is actually a Python library, open source Python library, which is designed for audio and music analysis. It has a lot of tools, functionalities, and methods to work with audio data, making it very easy for you to extract information from audio files, right? A lot of these software tools that are basically now using audio and ChatGPT, they've combined audio and ChatGPT to make sure that ChatGPT is able to respond to audio commands, not just text commands. They are using librosa to actually translate. So librosa is a very popular library for audio processing, music analysis, and because it can do feature extraction from audio, it is one of the primary, very important libraries for machine learning applications involving audio data. So librosa can load audio files in various formats. It could be WAV, MP3, JPEG, JPG. In fact, even if you give it a video file, it knows how to extract the audio from a video file, right? So that's also very interesting. And it provides a convenient way to manipulate and analyze them. For example, if you want to increase the bass, right, what we call bass in, let's say when we are riding in a car, we want to increase the treble or the audio or the volume or the bass, things like that. You can do all those manipulations with librosa as well. And finally, the best feature for machine learning is that you can extract a wide range of audio features like treble, bass. You can extract these things out. What is the frequency? What is the count of different beats getting played? What is the accuracy or speed of the beats? Such as Mel frequency, cepstral coefficients. These are basically very domain specific, audio specific values. So you can find them out. Chroma features, tonnets, etc., etc. These are essential for tasks like speech recognition, genre classification, and audio fingerprinting. I hope this makes sense to all of you. Yes, no? Guys, all of you. And that is the interesting thing about Python, right? No matter what kind of data, what kind of challenge you have, you can be sure that there is a library that, experts or people who've been working with the same problem for a lot of years have created for you. And you can exploit that library, use it for your advantage in a very simple and easy to work way. You don't have to build things from scratch. You can use things that people have already developed, and you can, take it to the next level of complexity. Okay. So I just loaded, I have a lot of files you can see here in this particular folder. I have all of these call records, right? .wav. I have all of these interesting call records that we are going to work with today. So I just loaded one of them using librosa, and you can see I can. See, I don't think you would have been able to hear it. Did you guys hear this? The call, the small 6-second video. I mean the audio. All of you heard it? Great, awesome. So this is the kind of calls, first of all, that 911 receives. A very interesting aspect of this is people like us might not be able to even understand these calls because these are distress calls. These people are under a lot of pressure, under a lot of anxiety. They might be in a very life or death situation, and they might not be able to understand, or their brain is not in the right mindset to even speak, right? But computers can actually do this much better, right? Because once the audio is recorded or the audio is coming through a channel, computers can obviously process that better, right? Let's try if we can hear another audio, right? This audio.
I'm Dylan Pearson, and I just killed 2 people.
See, this guy actually confessed his murder. He said, I am XYZ and I killed a few people, right? So these are the kind of calls, and you can easily see this printed from Librosa Wave Show. Remember, these were the things, if you've ever edited any music video, if you've ever uploaded these Instagram reels or things where you can edit the audio and video parts, this is how it is represented, right? Very interesting way of representing audio. This is not having the knowledge of the text. I can copy paste the same thing, same frequency, same audio, and have a completely different thing to say. So this is just the representation of frequency, or, if something was spoken in a certain point of time or not. So that is what it shows, right? Now, because, okay. So Shweta, what we did is first we imported all the libraries. Then we had our file name, which we want to extract. This plt.figure is just to show this figure, right? This is a matplotlib command. We are initializing this figure object, this whole template we are creating. Then we are loading the file, this particular audio, using librosa.load. It is giving us the data as well as the sample rate, right? This is the data and the sample rate. So sample rate is the time aspect of it, the frequency, and data is what it needs to plot. Okay. If you want to see what data looks like, this is the data. It's purely numbers. And this is the sample rate, 22050. So this is the part. Yes, matplotlib is used for visualization. Sumit, that is correct. And then librosa display.wave show. This is what we are adding to our PLT figure, matplotlib figure. This is what we are adding. It internally uses matplotlib to create this chart, this particular diagram. And then we are also initializing the IPython display audio player. So IPython is basically interactive Python. Right now we are working in an IPython notebook, right? Jupyter Notebook is an interactive Python notebook. So this interactive Python also provides other features like looking at images, videos inside of Python. So here we are using the audio capabilities of it to play audio inside Python. I hope that is clear, Shweta. Right? So this is just another example of trying to play another file. Now, once we have this audio file, right? Once we have this audio file, it gives us data and it gives us sample rate, right? If I try to print the audio data that I just showed you, it's actually printing numbers, right? You can think of these numbers as how much does it go above zero? How much does it go below zero? Does that make sense? See, this has positive and negative numbers, right? 0.25 shows how much does it go above zero. And these negative values actually show the bottom side of things, right? So you can actually visualize librosa audio data simply like that. But now we don't want to work with this data because this data only has frequency, right? It can show us how much emergency was the caller in. Were they hurrying? Were they saying a lot of words in a very less time span? Or were they very cool and calm and composed and, you know, they were speaking very nicely or very slowly in a very, you know, I would say laid back manner, right? That this data or this particular numbers can tell, but we need more features, right? That is why we have the librosa feature attribute, which can extract different kinds of features. This is the feature that we were talking about. Unfortunately, I also don't come from the audio background, so I don't know what MFCC exactly does. But through different research papers that we went through, we basically got to understand that MFCC is a way to introduce context of the call and, you know, different kinds of pitch, high or low. Were they very excited? Were they not? What was the maximum information or feature you can detect from this data? That is what MFCC does. It is one of the standard benchmark features to analyze audio. Now, I passed the librosa audio data. This was my sample rate, and this is my hyperparameter. So 60 frequency is what I want to sample this MFCCS for, right? When I'm looking at this particular feature at any point of time, I am looking at 60 sections of the sample rate, right? Don't worry about this factor, but just understand this at a top level. If you increase this value, then you will be able to get more granular features, right? If you decrease this value, you will be able to get a very smoothened or top level features. It's just like if you look at a stock price at a, let's say, monthly level, you will see a smoother curve, right? But if you look at that same stock at an hourly level, you will see a lot of changes, ups and downs, etc., etc. Make sense, guys, all of you? If I look at a shorter time period, at a shorter interval, I will see a lot of upward movement, downward movement, and a lot of jerks, breaks, ups and downs. But if I look at it at a larger perspective, I will see a very smoother curve, a very consistent curve in that regard. So this particular feature or parameter affects the feature that way. Okay. So I apply this. Okay. Now you can see 60, 259. Okay. This is for one particular audio data. By the way, guys, if I check this librosa audio data and you check the length of it, it gives you this value. If you divide it by 60, you get 2205. And then there is a multiplier with the sample rate, librosa sample rate, that will give you this 259. Okay. So there's with some addition and subtraction with you considering the sample rate and the frequency monitor, you will get this 60,59. Okay. So you can see there are 60 rows and in each row, there are 259 columns of features that are coming. Clear, all of you? Can we move forward now? Yeah. We just translated this entire thing into a feature extractor that takes a file name, loads that file name with librosa, extract these features for the same 60 frequency, and then does an average application. So I don't need this whole thing, right? I don't need this whole thing. I am just converting this entire data. This will be averaged into one single value, and I will have 60 features for each audio. Okay, so if you see this function, I'll just quickly call this function and pass a particular file name. Let's say audio file path is what I access. See, what is the shape of this? 60, right? Because these 259 have been compressed into one single value. Okay. Now I do that in a for loop. I will call this particular function throughout the data frame. You can see df.iter rows. That means I will go through each and every row, find the audio dataset path. Remember, our df had the audio path. See, file name. Our data frame had the audio path. It is the first 6 seconds. Okay, all the audios have been cut down in the first 6 seconds because that helps the computer understand if this is a serious or non-serious call. If the computer has to hear the entire conversation and then take a decision, then it doesn't make sense, right? So first 6 seconds only. And then I basically extract this feature for the entire data set. Okay. So if you see this, I have these 60 features, 60 values for each row. I'll just show you quickly. Final df.log0. Let's look at the feature. What is the shape of this? It is 60. So for each row, I have 60 parameters, right? 60 features. And I have the false alarm or non-false alarm column also, right? Was it a false alarm or not? Now I will train test split my data, right? I will train test split my data to get my X and Y. First of all, X and Y, what is my input? What is my output? So I see that 709 is my number of rows, number of samples I have. And for each case, I have 60 individual features. And Y is my output, which is the false alarm. Then I will go through my train test split. I will split my data where the test size will be 20%. You can play around with this, 10%, 30%, etc. Then because my data had imbalance, basically it has class imbalance problem, then I will resolve that class imbalance using the imbalance learned library of Python. I will do oversampling with synthetic minority oversampling technique, SMOTE technique. What is the full form of this? Synthetic minority oversampling technique. Using this, I will resolve the imbalance. And that will basically bring my both classes, false alarm 0 and 1, to the same length. False alarm column that let's say originally was 90% of one class and 10% of the other class. I am oversampling. So I will make this 10%, I will increase it in such a way that they become 50% and 50%. I am trying to get or achieve balance in my data. Clear, everyone, so far? All of you guys. Great. Once I have handled my imbalance problem, I am now building a machine learning model from scratch. Okay. I import TensorFlow, the sequential layer. Sequential layer is the generic artificial neural network creation strategy. So what it will do is there'll be layer 1. The output of layer 1 goes to layer 2. The output of layer 2 goes to layer 3, like that. Why is it called sequential? Because there is a sequential pass of data. From layer 1, it will never go to layer 3. It has to go through this route. Is that clear? All of you? Yes, no? Sequential layer. Densely connected layer, explaining that in a very detailed manner will be, out of scope for this particular time that we have for the bootcamp. Sumit, sequential, what we are talking about, the sequential layer is basically defining the architecture of the neural network. Okay. If you look at a neural net, if you look at this image, see, input comes here, then goes here, then from here it goes to here, from here it goes to here, from here it goes to here. See, there is no skip connection. It's not like from here it will go directly here, from here it will go directly here. No, right? It has to go through this route. That is why it's called a sequential architecture. I hope I'm clear. Okay. So there are different kinds of layers that fuel the good training or high performance of the neural network. We can discuss this more when we are, when you're in the class and we are discussing that at a higher depth. But for now, just understand that these are different layers of a neural network that help better training. So I create this neural network. I initialize the sequential layer. Then I first add the first layer, to which I'm giving 512 learning new nodes, right? So remember, my data size was 60. I had 60 features for each audio file, right? These 60 features will now be connected to 512 learnable parameters in the first layer. These 512, which you see this part, 512, are again connected to 512 in the next layer. So again, 512. And finally, it's also connected with another 512 parts. And post that, I have a single neuron. That means information will first increase from 60 to 512. There will be an expansion of knowledge or information. Then there will be feature extraction, learning, tuning, understanding the model, adjusting things. Then it will be compressed back into a single value, which will basically predict false alarm or not. Is that clear? All of you? Yes, no? Right? I initialize this. I create or basically design my neural network. First layer, this takes input and has the first hidden layer. We are making it, Shweta. So just think about it. If there are 3 neurons in the first layer and there are 5 neurons in the second layer, and each neuron in the first layer is connected with each neuron in the second layer, how many total connections will we have? 3 into 5, which is 15. Make sense? So if you see this image, can you see 3 inputs are connected with 4? Then these 4 are connected with just 4 only, right? But neural networks can be designed in a much more fashionable way. You can have an increasing layers. You can have something like this, see? Much more complex. Right? You can have something like this. There is a reduction or compression of information. And then eventually there is further compression towards the output. Right? So that is the architecture that we are designing for now. You can play around with this architecture. You might be actually able to achieve a better model if you tune the architecture a little bit. Harshit, to be very honest, that is out of scope for this bootcamp. We have another 10 minutes remaining. If I start explaining that, I need a pen and a paper. I need mathematical equations. I need to give you the understanding of the human brain, and there's much more to it. Okay. So understanding neural network mathematics, that's going to be not possible today. Maybe in another bootcamp, we can just decode the entire neural network. Okay. How it works. It has differentiation, partial derivatives, chaining of equations, lots of it. Okay. Sir, does it segregate based on patterns to further layers? Yes. So neural networks are basically designed in such a way that initial layers actually have low level features. Then layers in the center or in the middle will have, let's say, medium features. anything above low. And then finally, last layers will have high level information. Okay, so feature extraction at layers of neural net. If I see that, let's look at an image. Right, see this, very interesting. Human image. Okay, when it is looking at a human image, the initial layers are responsible for identifying shapes, straight line, curved lines, diagonal lines. Then the next layer, the second hidden layer, that is identifying medium level feature, like the next higher level features. So nose, eyebrows, ears, etc., etc. And the final layer actually combines these and makes high level features, which generates entire face. So every layer of the neural network is basically responsible for identifying higher level features than the previous layer. I hope that is clear, all of you. Harshit, we will evaluate efficiency, right? I mean, how good or bad the model is, that we will be able to figure out using the different metrics we have. So after building this model, I am going to train this model. Okay, I'm going to use Tensorflow Training. I have compiled the entire model. I have passed my training data, and I am trying to build this model. Over time, you should see that the loss, the difference between the actual prediction, basically actual result and prediction, initially, this will have some error, right? Then as the model learns, this error is supposed to reduce. Shubhankar's question is, what is training accuracy? So performance on training data that the model has learned from, that is your training accuracy. Okay, then there is similarly testing accuracy. So whatever your performance is on testing data that the model has not learned from, that is your testing accuracy. Okay, makes sense, Shubhankar? Right? So what should happen is, over time, my model should keep improving. It should make lesser mistakes. It should understand predictions better. Okay. So that is why we actually evaluate this loss. See, first loss was 9.95. Then loss became 0.4504. Then 3877. Then it increased slightly. Then it again decreased. Then it again decreased. At a top level, it should keep decreasing. There might be minor jerks here and there, but overall, my loss should keep decreasing as my training goes on and on. And finally, once I have this, once my model is created, I will predict using my model on my test data. Now remember, test data is data that the model has never seen before. I will never want to check the performance of my model on the data that it has learned from. If I give you 10 problems to solve in the class, I show you solutions of it, I tell you how the solutions are derived, I give you the answers, and I give you the same 10 questions in the exam, obviously you will score well. But if I give you 9 or 10 brand new problems, right, your performance on those brand new problems tells me if you've learned the concept or not. Make sense, guys? Yes, no? Right? So we always want to check the performance of my model specifically on testing data. This is the performance that I can trust. Performance here can be just because the model is complex enough to be able to memorize all the answers, right? And that is truly possible in neural networks. If you create a very complex neural network, after a certain threshold of complexity, the network will start to memorize answers to all the training data. It will be 100% accurate, zero loss, zero error, right? But it will perform very poorly on the testing data because it has not understood the data, the logic. It has memorized the answers, and memorizing never works. So now I do a prediction on my test data and I see my errors, right? I see how much error that I am getting from my model. So how do we know how much error that we are getting? Just think about this. YPred. These are my predictions. So when you look at this, this is 10 to the power minus 1, by the way. Okay. If you access this value and try to convert this into a float, right? This is the value 0.5349. What does 0.5349 mean? It actually means my model is not sure if it was a false alarm or not, right? If I look at this 0.50, if I look at this 0.52, now this value, see how interesting this value is. It is 3.21 into 10 to the power minus 30. So this is 0.000000 and somewhere 321 will start. So this value is very close to 0. Yes or no? Guys, everyone understand this? That means my model is predicting that false alarm is 0 for this case. That means this call is not a false alarm. This is a genuine call and we should pay attention to it, right? So in cases like these, it's very easy to decide. But remember, in cases like these, it is very difficult to decide. So here we use some kind of manual intervention. See, I am okay with getting some calls that were false alarm and still treating it better. Okay, but I am not okay with getting a non-false alarm call and ignoring it. When I say that a call is false alarm or when a call is not a false alarm, I want to be very sure when I am saying that it is a false alarm. I cannot ignore a call and have a poor prediction on it. So I will not consider 0.5 to be the central value. If I want to be extra sure, I will have a very higher threshold. I will consider a larger threshold to consider something as false alarm. If I'm predicting some call as false alarm, I want to be extra sure and not, make a blunder. Okay. So instead of 0.5, I will analyze the distribution of things and I will see that I should take a higher threshold. That is why I will say 0.65. You can have 0.7, you can have 0.8, depending on your choice. How strict you want to be, you can play around with this parameter for that. And then you predict the binary result. If it is greater than your threshold, then you will consider that as a false alarm. If it is less than your threshold, then you will consider that not as a false alarm, right? And then this is the confusion matrix that helps us understand how good or bad our predictions were. So these two sections, actual 0 means it was not a false alarm. I also predicted that it was not a false alarm. So 105 such cases. Actual 1 means it was a false alarm and I was able to detect it was not a false alarm in 5 of the cases, right? So out of 12 cases which were false alarm, I was able to detect 5 such cases that were a false alarm. I predicted them as false alarm. I could not detect 7 cases. Okay. And out of 130 non-false alarm cases, I was able to detect 105 non-false alarm. 25 I predicted as false alarm. Okay, that is what the confusion matrix says. Obviously, you need to dive deeper into the confusion matrix, understand this a lot more. But with the constraint of time, I would like to end the bootcamp session here. If there's any questions, please let me know. And I hope all of you enjoyed, learned something new, and had a lot of fun on this session. What percentage of efficiency is actually good? So see, out of all the possible false alarm cases, if you are able to detect 50 or 60% of them, right? If you are not making mistakes in false alarm cases, whenever you are predicting false alarm cases, you have to be very, very sure. Things like 99% of the false alarm cases. So when I say a call is false alarm, I should be 99% correct. When you get that kind of efficiency, then it's a good model to be deployed to production. Harshit, I hope I was able to answer your question. Great, guys. For any further questions, you can connect with the Ivy team and place their questions. They will connect you with me and they will help you. I mean, I'll be able to answer your questions. Okay. Thank you so much, guys, for your time. I hope all of you enjoyed this bootcamp / webinar and you got to learn something new.